In today's lesson, we're going to look at a very interesting concept known as the laws of universal gravitation. Now, let us take a brief story to enable us have a broader understanding of what this law entails. Okay? Now, long before the time of Newton, astronomers, that is, those people who study the universe, its objects and how it works, had discovered that the planets of our solar system revolve around the sun. Now, you can see that the planets actually revolve around the sun, right? Okay, and their motions were predicted very accurately, but there was no real understanding of the reasons for these motions. Now, Newton came on board. Isaac Newton was sitting under a tree one fateful day, and then something happened. An apple fell from the tree. Isaac, being a very smart person, was inspired as he saw that apple fall to the earth from the tree. Now, Newton, upon observing this apple, he began to think, the apple is accelerated, right? Now, since its velocity changes from 0 as it is hanging on the tree and moves downward towards the ground, thus, by Newton's second law, there must be a force that acts on the apple to cause this acceleration. Now, he said, let's call this force gravity. And the associated acceleration, the acceleration due to gravity. And when I mean the associated acceleration, I mean that of the apple, alright? Now, because definitely the apple will fall down the tree, and the apple will therefore have an acceleration. Imagine the apple tree is twice as high. Again, we expect the apple to be accelerated toward the ground, right? So this suggests that this force that we call gravity reaches to the top of the tallest apple tree. And so he related this to the motion of the celestial bodies. Newton knew that the force which caused the apple's acceleration must be dependent upon the mass of the apple. So, for Newton, the force of gravity acting between the earth and any other object is directly proportional to the mass of the earth, directly proportional to the mass of the object, and inversely proportional to the square of the distance which separates the center of the earth and the object. Now, he gave an expression to explain this, which is F varies directly to the product of the masses of the two bodies. Let's say the first body to be mass m1 and the second to be m2, and inversely to the square of their distance apart. Okay, now this can as well be written as F equals G m1 m2 over r squared. Now here G, okay, is the constant of proportionality known as the universal gravitational constant, and it is given as 6.67 times 10 to the power minus 11 Newton meter square over kilogram square. It is termed a universal constant. Why? Because it is thought to be the same at all places and all times, and thus universally characterizes the intrinsic strength of the gravitational force. Now, the numerical value of G is very small, which is basically the reason for the force of gravity to be the weakest force in nature. We have seen that in the universal law of gravitation, the crucial quantity is mass, right? The word mass. In popular language, mass and weight are often used to mean the same thing. In reality, they are related but quite different things. What we commonly call weight, this weight, is really just the gravitational force exerted on the object of a certain mass. Thus, the weight of an object of mass at the surface of the earth is obtained by, so we can get our weight, which is obtained by simply multiplying the mass m of the object by the acceleration due to gravity, g. We can relate this to the force of gravity, that is the force of attraction, which Newton spoke about. And we can equate the both of them to get the actual acceleration due to gravity, which is g in this case, right? So now if we do that, we can get g. Now Newton already gave us his formula. So now if we equate this to the gravitational force and the weight, we have g m1 m2 over r square equal mg. Now when you cross multiply, right, you get mg r square equal gm1 m2, right? So divide both sides by mr square to have g standing on its own. So we have g will equal gm1 m2 over mr square. When you divide through, you get, so m will cancel one of the m. Then we have g to be equal gm1 over r square. As easy as that. But if we are trying to get the magnitude of the gravitational force that is acting between an object at the surface of the earth, okay, we are going to be considering the mass of the earth and that of the body. Now we can easily represent this using Newton's law again as F equal G. In this case, we are considering the mass of the earth, remember. So we have this to be ME, then the mass of the body, let's say M over R square. So if we are relating this force to the weight of the body, okay, our M1 can be written as ME, alright, while the arrow would now be the radius of the earth, RE. Okay, now we assume the earth to be spherical and neglect the radius of the object relative to the radius of the earth in this discussion. Okay, now Newton's law of gravitation was preceded by three important discoveries about planetary motion. Now this was done by the German astronomer Johannes Kepler. Kepler was one of the early astronomers whose extensive study found the regular pattern of motion of planets. Now the planets are actually orbiting around the sun in their orbits. Okay, Kepler's first law of planetary motion says that the path of the planets about the sun is elliptical in shape. Now you can see that these planets are actually orbiting around the sun, right? And it's making the path in which they are moving is actually having an elliptical shape, right? You agree with me now, right? And he said that the path of the planets about the sun is elliptical in shape, with the center of the sun being located at one focus. All right, now the sun is the focus here. It is immovable. The mass of the sun is bigger than the mass of other planets, and so it is immovable. All right, okay, so Kepler's second law says that an imaginary line drawn from the center of the sun, let us put this as the center of the sun, okay, planet is actually moving. So let's see if we can capture the middle, the center, right? So this is the center of the planet. Okay. Now according to Kepler's second law, at the center of an imaginary line, which is this line, for instance, from the center of the sun, just like we've done here, okay, we'll sweep out equal areas. We'll sweep out equal areas, right, in equal intervals of time. And so that is what the Keplers second law simply implies. So we can say that the planet moves faster when it is nearer to the sun. And so since Mercury is closer to the sun, let's say this planet that is closer to the sun now, it will move faster than the other planets, right? Okay, so Kepler's Dead Law says that the ratio of the squares of the periods of any two planets, right? Now let's say the periods P1 of the two planets involved, P2, with their squares, is equal to the ratio of the cubes of their average distances from the sun. And so we can say arrow cube of the first planet over the second planet's cube. Okay, so we have been able to represent Kepler's Dead Law with this mere equation. Now there's something we should take into account. There are 5 fundamental forces encountered in nature. We have the electric and magnetic forces, gravitational forces, and the nuclear forces. This nuclear force is further divided into 2, the strong and weak nuclear force. So we have the strong and the weak nuclear force. The gravitational attraction between two objects is very weak. Hence, we hardly feel it in our everyday experience, okay? The electric and magnetic forces may be combined to form the electromagnetic force, which you probably might have heard of. Now, the difference between the electric force and magnetic force is very thin. Electric force is the attraction between electric charges, while a magnetic force may be regarded as an extra electric force that acts whenever charges are in motion. So as a result of this close relationship, it is justifiable to say that we have only 4 fundamental forces. For the nuclear force, the strong attractive force of the nucleus is called the nuclear force and is responsible for binding together the protons and the neutrons in the nucleus. Now, this is the strongest of all the forces. On the other hand, the weak force only shows up in certain reactions among elementary particles. As the name suggests, this force is very weak. Now, it is the weak force that causes radioactive decay reactions, that is, reactions that involve the spontaneous breakup of a particle into several other particles. Though the nuclear force is not fully understood today, and the study of the nucleus and its associated problems is the concern of nuclear physics. Now let's take a simple example to broaden our understanding on what we've discussed on this Newton's law of gravity. Now, we have a simple example that says, what is the gravitational force between a 75 kg man and a 60 kg woman separated by 10 meters? Let us see how this works practically, okay? Now, we have our 60 kg woman and our 75 kg man. Now, the question says, what is the force of attraction between these two, separated by a distance of 10 meters? Straight to the point, right? Okay, in order to solve this, let us list out our parameters that is given in the question. Now, you know already from what we discussed that G, which is the gravitational constant, is given as 6.67 times 10 raised to the power minus 11 Newton meter square per kilogram square, right? Now, the mass of the man, let's say M1, was given to be 75 kg, while that of the lady as 60 kg. Then, do not forget the separation, the distance between the both of them, okay, which was given to be r, which is given as r equal 10 meter. Right, now that we've listed out our parameters successfully, we can apply Newton's law of gravity, right, into this question. So we have it to be F equal gm1 m2 over r squared. From here, it's very easy. All we need to do now is impute our values into this formula, and voila, you get your answer. Easy peasy. Now let us get right to it. So we have F, imputing our values. G is 6.67 times 10 raised to the power minus 11 times the mass of the man, which is M1, 75, times M2, which is that of the lady, 60, over r squared, right? And so our r here is 10. Okay. Now if you solve this, you're going to get 3 times 10 raised to the power minus 9 Newton. Okay? And that is it. We've been able to get the force of attraction between the two of them. Now you can see that this force, the force of attraction between the both of them is quite small, and that's why they don't really feel it. It's not like it isn't there, but because it is very small, they don't really feel it, okay? And with this, I'm sure that you have a clear knowledge on the laws of universal gravitation, and I'm very sure that wherever you go, you can easily defend this. Now, if you have any question on what we've discussed so far in this lesson, kindly drop your questions in the comment section below.